All right. So last time I promised that today we'll be doing Lie groups, but then I changed my mind, and I think we'll continue for one more class with symplectic manifolds. So this is still this chapter 2, which is continued. And I would like to tell you several things about it. First of all, let's say M omega is symplectic. And let me recall that Hamiltonian vector fields. So these are vector fields defined in the following way. So vector fields on M with the property that there is a smooth function such that omega evaluated on the vector field, and we decided with a sign is equal to minus dh. In any event, that's an exact one form, plus dh or minus dh. So I think we have to choose minus dh. And here is a notation. So if you are given a function h, then because omega is non-degenerate, the corresponding Hamiltonian vector field is uniquely defined, and so we denote it by VH. So once you're given H, you know what VH is. It's not quite the same the other way around, remember. So we know the Durand differential of H, and if your manifold is connected, then H is uniquely defined up to a constant. So there are actually there are many H's which correspond to the same V, but to each H corresponds only one V. Right? So a small proposition about the properties of this construction. So suppose I take a Hamiltonian vector field which corresponds to a function f, and I act by it on another function g. But then it turns out that this is the same as minus vg of f. And this is also the same as omega evaluated on VF VG. So this is a kind of small technical statement. It is a very easy proof. So I like those one-line proofs. I don't know whether I'll really fit it in one line. So VF of G, what is it by definition? Right, this is the contraction of VF acting on the differential of G. So this is more or less a definition of how V acts on G, and this is equal to. And here I'm using the definition of a Hamiltonian vector field. So this is minus iota of VF, and here iota of VG of omega. So that's because this gadget is simply equal to omega of VG dot, right? And now this is the same as minus omega of VG VF. And this is the same as plus omega VF VG. So I proved that this guy is equal to that guy. And now just a similar argument, right? You can exchange F and G. The right-hand side is skew symmetric. This means that you just have to change the sign. So I don't need a separate proof for this middle term. All right. So this motivates the following definition, and already in the exercises of last time, you've seen some version of that definition, and maybe many of you know it very well, but let me still say it. So, so we define something which is called a Poisson bracket. So this is a bilinear map.
Sorry, in our preposition, we think about vector field like a differential operator, yes?
Yeah, sure. Yeah. A vector field is a first order differential operator which acts on functions. For instance, yeah, let me put it somewhere here. So a vector field on a manifold is something like this, right? And then this vector field acting on a function f. It is the sum vi of x df dxi. Right. Yeah. This is the first order differential operator. You can also, by the way, maybe that I should also say. So maybe, yeah. Sorry, I kind of destroyed my slide. So Vf of g is also the same as the Lie derivative of Vf acting on g. And I think last time when we were discussing Cartan calculus, one of you mentioned that this is the action on functions is just the action of vector fields by differential operators. So this is true. So you can use either of those two options. So they're both equivalent. So any other questions about Cartan calculus? Yeah, we'll be coming back to Cartan calculus relatively often. Already in the next problem set, you will have one more property of Cartan calculus. So it's very good if you ask more questions because we'll be using Cartan calculus more or less all the time. All right. So the Poisson bracket is a bilinear map. So from C infinity of m times C infinity of m to C infinity of m, which satisfies the following properties. So first, it is a Lie bracket. And by the way, how is it? Lie brackets, everybody knows what it is, or nobody ever heard of that, or how is it? You can write to me in the chat. Or so the first property is that it is skew symmetric with respect to the exchange of the arguments. And second, and that's the complicated property, is the Jacobi identity, which says that f gh plus g hf plus h fg is 0 for all fgh in C infinity. So so how is it? But I guess many of you have seen that property, or not really. Just for me, for the next class, it would be important to know. So tell me in the chat. Yes, you've seen it, right? So, and then the second property is the Leibniz rule, which says the following: f gh is fg times h plus fh times g. In fact, I write it for a product on the second factor for the second function, but since the bracket is skew symmetric, then it automatically implies that for the first function this is also true. Okay. So Now, claim, or maybe proposition. Let me say again, proposition. So we can define the bracket Fg by this formula, and it satisfies the axiom stated above. So there is a proof, and you know, there are several properties. Most of them are easy, and one of them is somewhat more difficult, and I will postpone the proof of a more difficult one. So first of all, so this operation is bilinear in F and G, right? This is more or less obvious, right? Because all the equation which determines VF or VG starting from F and G, this is a linear equation, right? That's this equation here. That's a linear equation. So therefore, VF is linear in F, VG is linear in G. So the right-hand side is bilinear in F and G. So this is easy. Now the next property is skew symmetry. If you change the order of F and G, you get a minus sign, but that's because omega is a two form, which means it is skew symmetric. Right? When you exchange VF and VG, you change sign. Now, the next property is Jacobi, and that's we postpone for a moment. And finally, what about Leibniz? So for Leibniz, we are actually using the proposition that we proved in the very beginning of our class. And this proposition is, in particular, is saying that the bracket of F and G is equal to VF acting on G. Well, now, of course, this is just a Leibniz rule for partial derivatives, so for first order differential operators, right? So if I write FGH, this is VF of GH. And we do know that there is a Leibniz rule for vector fields, right? Plus VF G. So this means that this property is also okay. Now let me give you a standard example. So you have seen in the exercises a sort of exotic example where the Poisson bracket is linear in coordinates. But I would like here to just to remind you or to tell you about the very standard example where M is R to N and omega standard is a sum of dpi with dqi in the coordinates Q and P. So then let me recall that last time we computed the Hamiltonian vector field for such an example. And for instance, VF is equal sum over n, df over dpi, d over dqi, minus df over dqi, d over dpi. So that's the formula that we derived last time. Well, now Fg simply Vf of G, and well, we get a formula which probably most of you or many of you know, or maybe not, I don't know, right? Minus df dqi dg dpi. Now maybe a remark. In this case, of course, it's very easy to just prove Jacobi by hand. So it's some kind of a little bit tedious exercise, but you just substitute the definition and you see that the Jacobi holds. So in this case, Eugenia, maybe you could, yeah, thank you. So in this case, easy to prove Jacobi. Okay. So so that's what I wanted to tell you today about Poisson brackets. So this is the example that we see now on my pad. That's the most standard example. But you already seen in the exercises somewhat more exotic example. In principle, there is a whole direction called Poisson geometry, where you study Poisson brackets rather than symplectic forms. And this is a somewhat more general story. For instance, I think in the example, in the exercises, you had a Poisson bracket on a manifold R3 on a space of dimension 3, which is an odd dimension, and there we know there are no symplectic structures, right? Because for a symplectic structure to be non-degenerate, we need the dimension to be even. So, so we conclude that Poisson geometry is a more general story than symplectic geometry, but we'll mostly focus on the symplectic case in this course. Right. Okay, so the next topic that I want to present is called Darboux theorem. Again, probably many of you heard of it or know it, but we're going to use Darboux theorem and then its versions or its upgrades in the course. That's why I thought maybe it's a good idea to speak about it and to speak about its proof. So the Darboux theorem says the following. So you have a symplectic manifold. And you choose a point in M. So the claim is that there is an open subset of M which contains M and the coordinate system, or you can say a chart. So the coordinate system, we're going to call it Q1, Qn, P1, Pn. Usually you center your coordinate chart at M. So the coordinates of M are all 0, such that omega restricted to U is given by the standard formula. So this is a very, very strong statement. So even if you already know it, so then maybe it's still good to talk about it a little bit. If you never seen it, that's probably the most important statement in symplectic geometry. So what it says, that symplectic manifolds don't have any local invariants, right? If you know the dimension, they all look the same, right? You can find the coordinate chart where your symplectic form has this standard form. So the only thing that you may look for are global invariants. For us, an example is if M is compact, for instance, then the symplectic volume, right? That's a global invariant. It knows about your whole manifold. Essentially, because of this statement or because of this observation, symplectic geometry essentially splits into two parts. So one of them is the big part called symplectic topology. So essentially, right, since you don't have local invariants, you need to look for global invariants, and global in some way means topology, right? You need to see what are restrictions on the topology of a manifold imposed by a symplectic form, what kind of things, what you can say on the topological side. So people study the topology of the group of symplectic morphisms and so on, right? This is essentially because locally you can't do anything, right? So then you need to go globally, and this is interesting, very challenging, and that's essentially not what we're doing in this course. So the other option, you can introduce more structures. So you can introduce, for instance, group actions. That's our plan for this course. And if you have a group action and a symplectic form, you may hope perhaps there are, again, some kind of local invariance. There is some kind of interesting local information, which would mean we are doing geometry and not only topology. So that's going to be our path. But essentially, the Darboux theorem, it tells you that you have to go either in one direction or in the other direction. And so we choose our direction, but in principle, of course, symplectic topology, that's a very big field. And that's also a very, very interesting and challenging field. But this, the choice, this dichotomy is defined by the Darboux theorem. So what I want to do, again, I don't know, maybe some of you have already seen the proof of Darboux theorem. So I want to talk to you about the sketch of proof. And what does it mean, sketch? You will see this means that I don't want to make some analytical details very precise. You can probably do it yourself if you want, or you can look up in literature, but you will see at some points my arguments, they won't be very, very detailed. They will be plausible, I hope, but they will be lacking a little bit of analytic rigor. Okay, so the proof consists of many steps. So that's an interesting proof. That's probably the first big proof we're doing in the course. We start in the following way. So we want to find a very good coordinate system near M, but let's start with some coordinate system. So x1, x2, n. Sorry, my color code. So let's say, let's choose a coordinate system on U. And as before, without loss of generality, I can think that 0 is my point M. Okay, so omega has any symplectic form in a local chart. It looks like this, where omega ij are some functions of x. So this is a skew-symmetric matrix, which depends on x. So, and I introduce the following notation. I denote by omega naught a new2 form, which is just constant. And I just take a value of omega ij at M. And I'm usually thinking that in this coordinate system, M is just 0. Right? So my coordinate system is centered at M. So dxi, dxj. So clearly omega 0 is closed, right? And it's not degenerate because omega ij at every point is non-degenerate, in particular at M is non-degenerate. So maybe I should say it. Omega ij of M, let's say determinant omega ij of M is non-zero. D omega 0 is clearly 0. And this means omega 0 is symplectic. So I got a new symplectic form, right? And now what I can do, you know, we discussed in symplectic linear algebra that if you have a constant symplectic form, you can just make a linear transformation. You can choose coordinates by linear transformation such that your two form acquires the standard form. Remember, we had that notion of a symplectic basis. So symplectic linear algebra implies that by linear transformation, find coordinates. So new coordinates q1, qn, p1, pn. So they are linear functions of x's, such that omega naught is equal to this sum. So you know, with this step one, we made some progress. It's at the moment it doesn't look very useful, right? So we took our form just at one point, and then we invented coordinates that at that point it would look like dpi dqi, but of course at other points omega is not equal to omega naught, right? So it's difficult to say how useful it is, but maybe just to make an illustration. So here is our manifold M. Here is the point M, and around it there is this U, and we had some kind of coordinate system X, whatever, X1, X2, and now we introduced a new coordinate system by linear transformation, QP, and with this new coordinate system, omega naught has this canonical form. Okay. Now, step number 2, I do the following. So I consider real parameter t between 0 and 1, and I introduce a family of two forms, omega naught plus t omega, and these are two forms on this neighborhood U, on this chart. What I can say about them? Well, first of all, I can say d omega t is clearly 0, right? That's clear. Then I want to discuss how non-degenerate they are. So let me do the following. Let me denote by sigma the difference between omega and omega naught. And notice that sigma of m is equal to 0, right? But that's of course because omega naught, that was simply defined using the value of omega at m. So maybe I rewrite omega t in the following way. So this is omega naught plus t times sigma, right? So this is just an equivalent rewriting. So now here is a claim, and that's for the first time I kind of cheat. I don't want to prove it in detail. So the claim is as follows. There is a possibly smaller neighborhood, U prime inside U, such that omega t is non-degenerate. On U prime. for all t between 0 and 1. So how do we know that? As I say here, I don't really want to make it very precise, but you know, first of all, everything is smooth, right, in our story that we decided from the very beginning. Omega naught is clearly non-degenerate. That's because omega was symplectic. Now, sigma is equal to 0 at m. This means, for instance, if I choose some kind of compact ball around m, then the derivative of sigma would have, or whatever, its norm, I choose any norm on that derivative, the derivative of sigma on that ball would have a maximum, and I can always make the ball smaller to make this maximum smaller. So I can choose a sufficiently small ball such that sigma cannot change too much in that ball. And this means that if sigma was 0 at m, so there would be some bound on the value of sigma within the ball. But omega naught, right, that's a non-degenerate matrix or non-degenerate operator. So you add to it something which is sufficiently small in norm, it cannot become degenerate. See, of course, this argument that I now spelled out, one would need to make it more precise if you really need to make it into an analytic statement. So, but roughly it is like that. So since everything is smooth and I can always consider some compact balls, I would have estimates on norms, and sigma is 0 at m. So then I can always choose a small neighborhood where sigma cannot be too far from being 0 in norm. Okay, so I don't know, is it convincing or not? At least you know, at the I don't want to do here this multivariable calculus, but still I want to know whether for you it sounds reasonable. Does it?
Yes, it's clear.
Okay, thank you. Okay, so you see what happens now. We knew that omega was symplectic. We knew that omega naught was symplectic, but now we have a whole family of omegas, those omega t's, which are symplectic on this u prime, right? So this whole family, omega t for t in 0, 1, is symplectic on u prime. Okay, so now step 3. So by Poincaré lemma. So I guess you probably know, right? The Poincaré lemma is saying that if you have a closed form on a contractible set or on some star-shaped domain, then it is actually exact, right? Then it's a total derivative of something. Do you know the statement? I guess.
Yes.
Good. Okay. So so we can find a primitive such that sigma is equal to d alpha. But I think actually it's easy to see more is true. We can choose alpha such that alpha of m is 0. Do you see? Do you see how this works? So why can I choose the primitive alpha such that its value at m is 0?
You can just shift it by a constant, for example.
Yeah. So if not, we can simply replace by alpha minus alpha of m, right? The differential of a constant, one form is 0, so it would do. So we can, without loss of generality, assume that alpha vanishes at m. Okay, so then there is a unique family of vector fields on U prime for t between 0 and 1, such that the following equation holds true. Omega t of Vt is equal to whatever. Now again, this minus sign is equal to minus alpha. Well, this is essentially because omega t, we know it induces an isomorphism between vector fields and one forms. So we're just looking for a vector field such that omega t produces a one form minus alpha. Note that alpha doesn't change with t, but omega t does change. Therefore, Vt a priori, that's something which, a vector field which depends on t. So maybe a name and a remark. So this Vt is called the Moser vector field. And a remark. So this Vt in general is not a Hamiltonian, vector field. That's because alpha is usually not exact. You know, the alpha is sigma. If sigma is non-zero, then it's not a Hamiltonian vector field. So even though the equations look somewhat similar to what we saw in the beginning of the class, so this is a family of vector fields which are not Hamiltonian. Okay. Well,
Excuse me, I have a question,
Sure.
if I may. So, do we know something about the dependence of V on T? Is it smooth? Well,
of V or of omega?
no, of so we have the family V of T of vector fields on U prime.
Yes.
So, is it smooth family?
Or in our business, everything is smooth.
Okay,
Yes.
so, but is it clear at the moment?
Oh, whether it is clear? Yes, I think it is clear because what happens, right? You have omega t. That's this family of two forms, right? So we know that they are all non-degenerate. So now the inverse will be smooth in T under this non-degeneracy condition. So we assume that sigma, and what was our argument? On U prime, sigma is small in norm in comparison to omega naught. So this means that, for instance, we can simply explicitly write the inverse as a power series, as a convergent power series in T. So we know that the T dependence of Vt will be analytic.
Oh, I see. Yeah, thank you.
It's even better than smooth. We can explicitly write a convergent, an absolutely convergent power series in T. Right. Well, what I have in mind, maybe I should say, right. So if I think of omega t for a moment as an operator, right. So we say, for instance, omega t flat is omega naught flat plus t sigma flat. Then what I need is this gadget. And then, you know, I can do something like this. I can say this is omega flat, and here 1 plus omega naught flat inverse T sigma flat, and everything is inverse, right? And this will produce for me a power series in T, which is absolutely convergent because the norm of this operator is strictly smaller than 1. That's how I would do it. Is it okay?
Yeah, it is pretty clear. Thank you.
Mm-hmm. Okay. Right. So now the next step, and sorry, like there are 3 more steps to go. So 4, 5, and 6. So it's a long proof. It's an interesting proof. Well, it will end in finite time, which is probably also good to know, right? So so I consider the following. Sorry, of x. So the following differential equation, right? So we want to run. We want to run an evolution with. So here is the point. Let's say x naught, and here is the trajectory. And at the point t, we get xt. And hopefully, this will define for us a diffeomorphism phi t, which maps x naught to xt. So we'll get back in a second to the existence, or maybe let me make a claim. Let me make a claim. So that's another statement, and that's the last statement where I need to cheat, or I don't give the full argument. So so there is a possibly again smaller neighborhood u double prime, which is inside u prime, such that phi t exists. On u double prime, and the image of u double prime is sitting inside u prime. So so here is our point M, and we have this u double prime, and then it is moved by the flow to the image. And this is happening for all t between 0 and 1. So why would this be true? This is essentially because of the following considerations. So we know that alpha of m is 0, and this implies that the value of the vector field Vt at m is also always 0. This implies, of course, that phi t of m is simply m for all t. So the point m itself, it doesn't move. But also by arguments similar to those that I had before. So Vt on a sufficiently small ball, Vt is actually small. So you know that even over the time period from 0 to 1, the point cannot move too far. So that's essentially. So I need an estimate on the norm, on the absolute value of my vector field, and I'm estimating that the point doesn't move too far. And here it's very, very essential. It's absolutely crucial that we made a choice of alpha with alpha of m equals 0. Because without that, of course, nothing would work, right? The vector field would simply move m, and together with m, all its neighborhoods, God knows where. It also, this estimate on VT, it allows you to control the differential equation and to say that it actually has solutions. You know that solutions of ODEs, that's a tricky thing. And unless you have some control over smoothness and over the norm of the vector field, then everything can happen, right? Your points will run to infinity, whatever. So smoothness is now guaranteed because we assume smoothness all the time. And I just discussed why the family VT is even analytic and not only smooth. But then we also need a norm estimate because otherwise our points will run away. So in the norm estimate, that's because that's a smooth function with value 0 at m. So near m, I can estimate, I can find sufficiently small ball where the values of its norm will be sufficiently small, simply by definition of continuous functions. Right. Okay. So you see, we now twice decreased the size. We started from some chart. We first decreased the size in this step 2 to make omega t non-degenerate. And now for the second time, we possibly reduced the size of the chart to make phi t exist. You know, like it's all very nice, but maybe a small informal comment. So the statement of the Darboux theorem is very clear and beautiful, but the proof that I'm presenting to you, because of all those considerations, is highly non-constructive. So in principle, you know that those Darboux chart exists, but you see already here, it doesn't look very good if you really want to implement that algorithm. So I think you need very, very special circumstances to be really able to compute a concrete map giving you Darboux coordinates. All right. So now the next claim that we'll try to prove. So d over dt of the pullback by this map phi of omega t is equal to 0. And this statement goes under the name of the Moser lemma. In fact, the original Moser's argument was invented for volume forms, as far as I recall. But this is a construction. This is a statement which is used very, very often in symplectic geometry. So, okay, so let's see why is it true. So we have d over dt of phi t star omega t. And now let me rewrite it in the following way. So I say that this is d over ds of phi star t plus s omega t plus s at s equal 0, right? This is, of course, just a triviality, some kind of formal manipulation, right? Well, this is equal to d over ds, right? And here I write phi t star composed with phi s. Or maybe I write it like this: t plus s star applied to omega t plus s at s equals 0. And now you know, maybe drawing would be good. So again, what I'm doing. So here is the point x0. It is moved to the point xt, and here it is moved further to the point t plus s. And so So this is a diffeomorphism phi t, which goes here, and this arrow is a diffeomorphism phi t plus s. So that's how it works. And I first take a pullback from t plus s to t, and then the pullback from t to x0. Why not? Now, why does it have an advantage for me? That's because now phi t star, I don't touch it. And now I compute the derivatives. First of all, the derivative here, the derivative over s, this is just a definition of a Lie derivative. That's the one that we saw last time. So this is L of Vt omega t, where I now put s equals 0 on omega. Plus, there will be, of course, a derivative of the s dependence in omega. So plus d omega t over dt. So that's the formula. Okay. Now, actually, we know what's the derivative of omega t with respect to t. So by definition, that was equal to sigma, right? Now, what about this thing? Well, as you can imagine, I'm using. Oops, sorry, what happened? Oh, yeah. Yeah, we're going to fix it later. So it's equal to d iota vt omega plus iota vt d omega. So that's the Cartan calculus, the Cartan's magic formula. And now this guy is 0, right? And iota of vt omega.
Excuse me, there is omega t.
Omega t, absolutely. Yes, that's essential. Yeah, you're right. And iota vt omega t, I'm sorry, I did something to my PDF. Right. So iota vt of omega t, that's this thing, right? And this is equal to minus alpha. That's, of course, was the whole idea of the Mose trick, right? So this is equal minus d of alpha, and this is equal to minus sigma. Now, this sigma and this minus sigma, they cancel out, and this is equal to 0, which is, of course, very good. Okay. Now, well, the last step. So the last step, number 6. Well, now we're going to use this formula. So it says that omega naught, which is, of course, phi naught star, which is just identity, right, of omega naught, is equal to phi 1 star of omega 1, and omega 1 was equal to omega. So maybe in more detail, what does it say? It says that the sum from 1 to n dpi dqi is equal to phi 1 star 1/2 sum over ij omega ij of x dxi dxj, or in other words, it says the following, that the Darboux coordinates are, and you take qi composed with q1 phi 1 inverse and pi composed with phi 1 inverse, right? So that's what you're saying. That's because I can also rewrite this identity in the following way. So omega is 1/2 omega ij of x dxi dxj is equal to phi 1 inverse star dpi dqi, and this is equal to dpi inverse dqi phi 1 inverse. So this is, so the right hand side is in the form that we want. So you can call, I don't know, if you want, you can call those coordinates whatever, capital Pi and capital Qi. And these are the Darboux coordinates that we were looking for. Of course, as I already said, that's a very, very beautiful result. It's a very nice result. I would say the only problem with it, it's highly non-constructive. So you need this, this map phi 1. And if you really want to construct phi 1, recall you need to invert omega t, you need to construct this VT vector field, and then, which is the worst of all, you need to integrate it. This t-dependent vector field VT, you need to integrate this differential equation here. So this is not a very constructive proof, but the outcome is very beautiful. So that's the end of the proof. Do you have some questions or comments about it? So for the rest of the class, I want to do some simple stuff. So I think we kind of worked enough with hard stuff. Now maybe some simple stuff. But by the way, have you seen that proof, or have you heard about the theorem, and have you seen the proof before, or what's just for me to orient myself?
I have a question.
Yeah.
In general, I read the book of the symplectic manifold written by Fukaya.
Yes.
Yes. He says something that, like, after Darboux theorem, people disinterested in symplectic geometry. Is it true?
No, I mean, let's say, well, it's right. It's not a mathematical statement, but what I told you before, right? After the Darboux theorem, you need to decide what are really the questions, right? Because people, let's say, were thinking about geometry using the example that they knew before, and that example was Riemannian geometry. Riemannian geometry has a lot of local structure, right? The space can be curved, or it can be whatever, right? There might be different things. So there in Riemannian geometry, or in pseudo-Riemannian geometry, there is a lot of study of how Riemannian manifolds look like locally. That's a big chapter. But in symplectic geometry, when it turns out that locally, okay, we are done, right? We now proved that Darboux theorem, and we are done. So then the question is what you do next. And as I indicated, there will be, there are two choices. Either you should look at global properties. You assume you have a symplectic manifold, and you want to say how do they look like globally. Locally, they all look the same. And on the other hand, you can add more geometric structures like group actions, and there you will see some local geometry again. And here on the chart there is a question where will we use the Darboux theorem, and in fact what will happen. Sorry. Go ahead. Well, you wanted to say something?
No, I didn't say anything.
Okay. Good. Then maybe you should mute your mic, unless you want to say. If you want to say something, say something. Okay. So then, and there is this question on the chart where we'll be using the Darboux theorem. Well, you will see we'll have to upgrade it, but it will be an easy upgrade, including group actions. And then the Darboux theorem will be helping us to understand the group actions on symplectic manifolds. So the geometry will reappear. So there will be some local data. So not all symplectic manifolds with group actions will look the same. However, the Darboux theorem already tells you that at least symplectic forms, they look the same. And now you should just figure out what to do with the group actions. So this will be a very essential part in our future study of group actions on symplectic manifolds. So from that perspective, and also in the next exercise in the problem set, you will have some version, some upgrade of Darboux theorem to some kind of manifolds called Lagrangian submanifolds. But by the way, Ian, could you put again the problem set 3 on the chart? Because I think people who came later, they cannot see it, right? Maybe it's a good idea to paste it on the chart again.
I was exactly planning to interrupt you to say that, and I'm going to do it now. So I'm doing it.
Okay, thanks a lot. Sorry for prompting it. All right, so
yeah, excuse me. I have a question.
Sure.
I just was to try to interrupt you before.
Yeah, yeah.
So my question is kind of, am I right that the idea of the proof is actually quite simple? So you produce a vector field that's straight your coordinates actually. So you just take.
I mean, yeah, you know, again, whether you qualify it simple or not, I mean, that's really up to you. Yes, it is in some way.
I mean, so the idea is to take. So I want to produce vector field taking omega t, and then just my coordinates is just straightening these vector field. So my coordinates is just straightening up this vector field. Yeah.
Yes, absolutely. So I mean, maybe we can look again at this equation, right? So there is this thing under phi t, and this is equal to 0, right? This sum. So it basically does say that the vector field Vt is transforming omega t by changing t, right? So the t derivative is equal to the Vt derivative. So Vt changes your coordinate system, right? Or it generates a diffeomorphism, which is gently changing your coordinate system with t. And now you want to flow from t = 1 to t = 0. So you're changing coordinate systems, and in the end, your original form now looks like omega 0. But omega 0, you know how to transform into the canonical form. So from that perspective, you're right. That's it. Yeah, you find a change of coordinate system which implements the change of time. And with change of time, you arrive at t = 0, and at t = 0, you have full control because that's a linear algebra problem. So yeah, that's correct. So maybe what I was saying was slightly misleading because I was stressing the difficulty of it. But of course, you're right. It's also conceptually, it's a very, very simple procedure. So you find a coordinate transformation which would flow you to the linear algebra problem instead of a complicated analysis problem. That's correct. All right. So finally, some remarks on submanifolds of symplectic manifolds. So let's say M omega is symplectic. So then, you know, similar to classification or to names that we gave to vector subspaces of a symplectic vector space. So there are names given to submanifolds. So let me call a submanifold in some way. let me denote it by S inside M. And we're saying that it is isotropic if the corresponding tangent space inside the tangent space to M is isotropic for all M in S. So in fact, it's easy to see that this is the same as omega restricted to S being 0. Recall that on isotropic subspaces, the two form vanishes. Now the two forms should vanish in all points. And so the restriction of a two form to submanifold is simply 0. Of course, it goes on in the same way. So we say that it is Lagrangian if TMS, TMM, sorry, omega M is now Lagrangian. And this is now equivalent to two facts. Again, of course, omega should be vanishing on S. And in addition, the dimension of S should be the dimension of M divided by 2, because that was exactly what was happening at the level of vector spaces. Again, similar, quasi-tropic if sorry, CMS is quasi-tropic and it is symplectic if TMS is symplectic. So we're going to need all those notions when talking about group actions. So that's why I want to give you those names. Now, perhaps let me finish with an example. And this example will be useful for the next problem set. So let me recall from the previous problem set. So we had the following setup. So Q is a manifold of, say, as I mentioned, N. And we take M to be a cotangent bundle of Q. So we know that it carries the standard symplectic form, which in a local chart looks like this. So simply dpi wedge dqi. So pi's are coordinates in the fibers. And the first observation is that this cotangent bundle has a 0 section. So this is Q, which embeds in M. And this 0 section, this is simply locally can be described as points QP with P equals 0, right? So that just because P are coordinates on the fiber, so simply put P equal 0. And it is obviously Lagrangian. So why is that? Well, the dimension is equal half of the dimension of M. And if you put P is equal 0, omega clearly vanishes, right? So So this follows from omega restricted to Q is equal to 0. Maybe a bit more interestingly, one can do the following. So let me choose f, a function on Q, and let me define a submanifold LF, which again in a local chart will look as follows. So this will be points Q1, Qn, and here I put df dq1, df dqn, and these are the values of p's. And this is for Q in Q, and this is a submanifold of T star M. So the claim is that it's also Lagrangian. And so this is because of the following. So the dimension of LF is clearly equal to the dimension of Q, and this is 1/2 of the dimension of M. But also, when we restrict omega to LF, what we should do, we should substitute instead of p's those partial derivatives, right? I think it's more elegant to rewrite it in the following way. So I first take away the Durand differential, right?
Without the wedge.
Oh, sorry, yeah, no wedge. I agree. Of course, why not? There is no contradiction with a wedge. Pi is a 0 form, but you're right, better without a wedge. And here it looks very nice, because the expression under Durand differential is the Durand differential of f. And we know that d square is 0. So this is 0. Of course, you can also prove it more directly. You will see that there you will have second derivatives of f, the Hessian matrix of f, which is symmetric, and multiplied by dqi wedge dqj, which is q-symmetric. And this would also give 0. So in this way, we have lots of Lagrangian submanifolds in the cotangent bundle. And I would like to end up with the following theorem. And actually, this theorem or sketch of a proof of this theorem is a homework. So the theorem is saying the following: that L inside M omega be compact Lagrangian submanifold. So then there is a tubular neighborhood of L, and another tubular neighborhood of L viewed as a 0 section in T star L. Sorry, I should put here V inside L, and a symplectomorphism phi such that Q omega y. Maybe I better, sorry, maybe I better say, yeah, diffeomorphism. Such that this map is actually a symplectomorphism. So you see, this is a kind of version of the Darboux theorem, right? Darboux theorem was giving you a kind of normal form of or symplectic form near a point. But now what this theorem is telling you is the following. So now you have your manifold M, and inside M is sitting a Lagrangian L. And then you're finding this tubular neighborhood U, such that you can identify it, right, with a tubular neighborhood of L in some standard manifold with a standard symplectic structure, T star L. And here you, well, let me see that I still have colors. Yeah, maybe yes. So this is V, and so the symplectomorphism maps U to V, right? So that's fine. So you see this is a very similar in spirit statement, and of course I don't want you to kind of work kind of for hours and hours, but maybe you should just take an inspiration from the proof of Darboux that we saw today and just try to imagine how it's going to work, right? So that's a very similar statement, and we'll need to use such statements from time to time during the course. So it's good to know what is easy, what is difficult. So what do you actually need to look at when you prove such a statement? So this is clearly proving this theorem is clearly a difficult problem, but try to think about it. And I think next week we're going to show you a solution. I think that's it for today. So next week, I promise again, we'll start looking at group actions, at groups and group actions. And I think now there is no excuse not to do it. So next week, certainly we're going to do it. And yeah, I don't know whether you have further questions about today's material.
I have a bunch of information.
Go ahead.
First of all, am I right that it's a little bit confusing? Am I right that in theorem M is any symplectic manifold, but not cotangent bundle of?
Yes, M is any symplectic manifold, and L is its Lagrangian submanifold.
Great. Okay, and now I have a little question, a small question about submanifolds. So
Yes.
When we discussed the linear algebra part, there was kind of duality between isotropic and quasi-isotropic subspaces.
Yes, that's true.
And is there any kind of duality in this case?
Let's say maybe, you know, it may be not a very good answer, but I prefer perhaps not to answer it immediately. There will be something like, I mean, depends on the interpretation. There will be something a little bit similar to the duality. You will see. But I prefer to answer that question maybe in 2-3 lectures from now. I'll try to remember it, but in any event, we'll come to it in our particular situations. So I understand it's not a very satisfactory answer, but we'll see. We'll see things similar to what you are asking for, but not exactly. Sorry for being cryptic.
Yeah, that's.
Mm-hmm. But that's a good question, and we'll see things inspired by that question later in the course.
Okay, and I guess the last one for me at the moment is about the Lagrangian submanifolds of cotangent bundle.
Yes. Sure.
Maybe it is a very silly question, but is there any other Lagrangian submanifolds of cotangent bundle?
Okay, like then maybe it depends a little bit on your, yeah, sure. Like let's say, yeah, maybe, yeah, right. Take any cotangent fiber, so fix Q.
Okay.
Right. It looks like a Lagrangian submanifold.
Sorry, what do you mean by fixing Q?
No, but I mean you have a cotangent bundle, right?
Yes.
So let's take a cotangent fiber, which means that I choose a point on the base. I choose a point of the manifold Q, and I'm looking at the fiber, right? It's a vector bundle. Cotangent bundle is a vector bundle. So over that point, we have the fiber is a vector space, which is just a cotangent space at that point. So it's clearly Lagrangian because now this form, the standard form on the cotangent bundle is dp/dq. Now, if I'm saying that QIs are fixed, their differentials vanish on the fiber.
Yes, of course, but yeah, I mean maybe something more interesting. So well, you have vertical ones, you have sections of, well, you have.
I think what you can do, let me see from the memory. You take a submanifold of the base, right? And then yeah, right. You have so I think you can do the following. Let's say I have S now a submanifold of the base. And now I'm taking points which are of the form S P, where S is in S and P in CSS, right? You have a tangent space to S and you take the orthogonal of that tangent space. So these are covectors which vanish on the vectors tangent to S. If I'm not mistaken, I think this must be Lagrangian. So this is a mix, right? Of
yes, yeah, this is something in the middle between
yeah.
and vertical ones.
Yeah, right.
Yeah.
Okay, more questions?
Yeah, thank you very much.
Professor?
Sure.
I have a question. Yeah, about like symplectic manifold in general in Russia. As I said, I read books from Fukaya. Fukaya is like a researcher on Riemannian manifold, but he met.
Fukaya is a researcher on everything.
I mean, sorry. Originally, he was Riemannian manifold researcher, but he met Gromov, and Gromov introduced him a symplectic manifold, and he described that Russian has very well familiar with symplectic manifolds, so that Gromov has no a lot on symplectic manifold. He described its characterization of Russian likes symplectic manifold. Is it true? Like he described so, but
you're asking me questions on the history of mathematics, right?
Yes.
Yeah, I don't know. These are very general questions, right? Yeah, sorry, no comments on that. I guess, well, depends on the person. Of course, that's true. There is a very strong school which originates from Russia, like starting with Gromov and then Eliashberg, right? But I mean, there are now, especially, I think that's the direction of symplectic topology, right? Fukaya himself is one of the world's most prominent symplectic topologists. So
I see. Yeah, thank you.
yeah, you're welcome. Okay, look, people, thanks a lot. And right, I'll see you then next week. We're going to talk about groups and group actions. Thank you.
Okay, thanks, Anton.
I'll now stop recording.